Hello everyone, Dr. Maddie here, and thanks for joining me today with another lesson on foundations necessary to express robot motions. In the previous lesson, we saw an introduction to screw theory and its applications and importance in robotics. We saw that integrating a constant twist over time gives us the configuration. We also became familiar with exponential coordinates of robot motions, and we saw that in order to define the screw axis, we need to understand angular and linear velocities. In this lesson, we'll study the concept of velocities in robotics, and we'll become familiar with angular velocities and twists and their applications in robotics. This lesson is part of the series of lessons on foundations necessary to express robot motions. More lessons will be added in the future, so by being a part of the Mechatronics family, you'll never miss a lesson. So without further ado, let's get started. A rigid body's velocity can be represented as a point in a six-dimensional space, consisting of angular velocity and linear velocity, which together is called a spatial velocity or a twist. From this, we can conclude that although a robot's configuration space is not Euclidean and thus non-flat and doesn't form a vector space, the space of the robot velocities always forms a vector space, which is a plane tangent to the robot's configuration space at any point on the C space. There are several ways to express angular velocities and twists in robotics that we'll discuss in this lesson. Unlike the space of orientations that is curved and cannot globally be expressed by three numbers without singularities, the space of angular velocities is a flat 3D space or a linear vector space tangent to the curved 3D surface of orientations at any given orientation. And thus, the 3D velocity space can be explicitly parameterized by three numbers without singularities. If we take the curved space of orientations, or big SO3, as a sphere, then the space of angular velocities is a flat 3D vector space tangent to big SO3 at that orientation. Note that the 3D vector space can be represented globally by three coordinates without any singularities. In order to understand the angular velocity concept, suppose a rotating body with the coordinate frame axes attached to it at time t and rotating with the body about an arbitrary axis passing through the origin by an angle delta theta. The axis of rotation is coordinate free for now, which means that it's not yet represented at any particular frame. A small change in the orientation of this frame can be depicted as this figure. Note that each of the coordinate axes is of unit length, so only the direction can vary with time. The rate of rotation of the moving body about the arbitrary axis can be defined as the limit of delta theta over delta t when delta t approaches zero. Note that the rate of rotation is analogous to the concept of speed in physics, which is a number compared to the velocity that has an amplitude and a direction. Therefore, the rotation of a rotating body about an arbitrary axis with a known speed of rotation can be visualized like this figure. The motion of the frame as it rotates about the arbitrary axis is according to the right-hand rule, and any angular velocity can be represented by a rotation axis and the speed of rotation about it. As the coordinate axes rotate about the arbitrary axis, the coordinate axes trace a circular path. For instance, if the coordinate frame axes shown in this figure rotate with a constant rotational speed about the arbitrary axis, each of the axes traces a circular path as it's shown for the x-axis as an example. From physics, we know that an object in circular motion experiences centripetal acceleration, and the linear velocity is in the direction tangent to the circle that can be calculated from the cross product of the angular velocity and the radius vector. We also saw this in the example of the salad spinner in the lesson about the exponential coordinates of orientations. Similarly here, the linear velocity of each axis is in the direction tangent to the circle, and it is the cross product of the angular velocity and the radius vector, which is the axis itself in this case. For example, for the x-axis, it's like this figure. So the linear velocities of frame axes rotating about an arbitrary axis with a known angular velocity are in the direction tangent to the circular path and can be calculated using these equations. Now let's see how we can define the angular velocity with respect to different coordinate frames. Now we want to express the angular velocity with respect to coordinate frames. We can choose a coordinate frame for angular velocity, and our natural choices are the space frame or S and the body frame or B. If the rotation axis is defined in the S frame, then the angular velocity expressed in the S frame can be written as this equation, in which omega hat S is the unit axis of rotation and theta dot is the rate of rotation about this axis. The axis of rotation is expressed in the S frame. A similar equation can be written for the angular velocity expressed in the B frame. We then want to find expressions for the angular velocities in the S and B frames in terms of the rotation matrix. Suppose that RT is a rotation matrix that represents the orientation of the body frame with respect to the fixed frame at time t that can be expressed in terms of its column vectors as RT equal to its column vectors. As we learned in the rotation matrices lesson, the column vectors of this rotation matrix are the coordinate axes of the body frame expressed in the fixed frame coordinates. Thus, the time rate of change of RT can be expressed as this equation, where bracket omega s is the 3 by 3 skew-symmetric matrix representation of the angular velocity expressed in the fixed frame coordinates at a specific time. As we saw in the exponential coordinates of the orientation lesson, we use this notation to eliminate the cross product. Also in the same lesson, we defined the set of all 3 by 3 real skew-symmetric matrices as little SO3, which is the Lie algebra of the Lie group big SO3 that we defined in the lesson about rotation matrices. In other words, little SO3 consists of all possible R dot when R is equal to identity rotation. With this definition, we can now write the angular velocity vector in S frame as this equation. So bracket omega s is R dot times R transpose. From the rotation matrices lesson, we know that the inverse of a rotation matrix is the same as its transpose. So R inverse is equal to R transpose, and thus we can write this equation. Now we want to find the angular velocity vector in the body frame coordinates. Note that omega s and omega b are two different representations of the same angular velocity omega. In the lesson about rotation matrices, we learned that one of the applications of a rotation matrix is to serve as an operator to change the frame of reference of a frame or a vector. Thus, we can find the relationship between the two different representations of the angular velocity using the rotation matrix and the subscript cancellation rule as omega s equal to RSB times omega b. RSB is the rotation matrix representing the orientation of the B frame relative to the S frame. Therefore, omega B can be calculated as R transpose omega S. Now it's easy to write the scusometric matrix form of the angular velocity vector in the body frame as this equation. R bracket omega R transpose is equal to bracket R omega. Proof of this equation is on the reading version on the website. In summary, equations relating R, which is the orientation of the rotating frame as seen from the fixed frame, and R dot to the angular velocity of the rotating frame, omega, can be written as these two equations. Omega B is the body frame vector representation of omega, and bracket omega B is its 3x3 scusometric matrix representation. Similarly, omega S is the fixed frame representation of omega, and bracket omega S is its 3x3 matrix representation. Note that omega B is not the angular velocity relative to a moving frame, but rather it's the angular velocity relative to the stationary frame B, instantaneously coincident with a frame attached to the moving body. This is from Newton's laws that the reference frames are always considered to be inertial. Also note that fixed frame angular velocity, or omega S, is not dependent on the choice of the body frame, and the body frame angular velocity, or omega B, is not dependent on the choice of the fixed frame. This is because although R and R dot are individually dependent on both the space frame and the body frame, the product R dot R transpose is independent of the B frame, and the product R transpose R dot is independent of the S frame. Note also that we can represent the angular velocity expressed in arbitrary frame D in another frame C if we know the rotation that takes the C frame to the D frame. To conclude this section, let's see some examples. In this example, consider that the humanoid robot, Pepper Robot from SoftBank Robotics, is rotating its elbow while keeping all other joints fixed. Then the linear velocities of the points on the forearm can be calculated from the cross product of the angular velocity and the distance of the point from the center of rotation. The distance of the point from center of rotation, which is the radius of rotation, can be expressed in the S frame as Ri equal to Pi minus P. Pi is the distance of the point from the S frame, and Pe is the distance of the center of rotation from the S frame. Angular velocity is equal to the rate of rotation, theta dot, in the omega S hat direction. Note that the points farthest from the center of the elbow have larger linear velocities. As another example, suppose that in terms of the axes of the space frame S, the body frame's x-axis and y-axis are in 0, 0, 1 and minus 1, 0, 0 directions respectively. An angular velocity omega is expressed in the S frame as omega S equal to 3, 2, 1. We want to find the representation of the angular velocity in B frame coordinates. For this, the two frames S and B can be drawn as you can see in the figure. Note that since we don't have the position information, we can suppose that the origins are the same and they are illustrated separately for clarification. As we just learned, we can represent the angular velocity in another coordinate frame using the rotation matrix representation of the orientation of one frame relative to the other. For our example, we can write omega B is equal to RBS times omega S. The rotation matrix representing the orientation of the S frame relative to the B frame can be calculated by taking the transpose of the rotation matrix representing the orientation of the B frame relative to the S frame as this equation. Thus, the representation of the angular velocity in the body frame can be calculated as omega B equal to R transpose times omega S. So omega B is equal to 1 minus 3 and minus 2. Now let's see what the concept of twists means in robotics. In the previous lesson, we saw that integrating a constant twist over time gives us the configuration. We now want to argue that a twist is in fact continuous change imposed over time. A twist can be defined as an angular velocity and the linear velocity of a moving body combined together into a compact six-vector. In the section about the angular velocities, we saw that pre or post multiplying r dot by r transpose results in the symmetric matrix representation of the angular velocity vector either in the fixed or the body frame coordinates. Let's find out if similar physical interpretations hold for the multiplications T inverse T dot and T dot T inverse. Suppose that S is the fixed or space frame and B is the moving body frame, and the configuration of the body frame B as seen from the space frame S is defined using the transformation matrix TSB as a function of T. Then we can find this equation for the multiplication of T inverse and T dot. Refer to the lesson on homogeneous transformation matrices to understand how to calculate the inverse of the homogeneous transformation matrix T. As we saw in the angular velocities section, R transpose R dot is the symmetric matrix representation of the angular velocity in B coordinates, and P dot is the linear velocity of the origin of the B frame expressed in the fixed frame S, and thus R transpose P dot is the linear velocity of the origin of the B frame defined in the B frame coordinates. This makes sense since R transpose SB is equal to RBS, and the multiplication of RBS and P dot S changes the reference frame from S to B from the subscript cancellation rule. For more information, please refer to the lesson about the rotation matrices and study their different applications. Therefore, the multiplication of T inverse T dot can be rewritten in terms of the angular velocity and the linear velocity as this equation. From this equation, we can conclude that the multiplication of T inverse and T dot represents the linear and angular velocities of the moving frame relative to the stationary frame B currently aligned with the moving frame, and more accurately, it represents the matrix representation of the body twist, which is the spatial velocity in the body frame and can be defined as this equation. Note that here bracket notation shows the matrix representation of the body twist. It's important to distinguish between bracket angular velocity and bracket twist because in bracket angular velocity, the bracket notation means the symmetric matrix representation of angular velocity, whereas in bracket twist, the bracket notation refers to the matrix representation of the twist. The multiplication of T inverse T dot is the matrix representation of the body twist that belongs to little SE3, which is the set of all 4x4 matrices of this form. Little SE3 is the matrix representation of the twist associated with the rigid body configuration in big SE3. In other words, little SE3 is the Lie algebra of the Lie group, big SE3, and consists of all possible T dot when T is equal to the identity configuration. In other words, the set of all 4x4 real matrices with a 3x3 little SO3 matrix at the top left and 4 zeros in the bottom row is called little SE3, which is the space of 4x4 matrix representation of twists. The top left 3x3 submatrix, as we discussed, is the symmetric matrix representation of the angular velocity. The top right is a 3x1 vector, which is the linear velocity of a point at the origin of the body frame expressed in that frame. We will use these matrix representations for the matrix exponential and logarithm for rigid body motions in the next lesson, as we did for the matrix exponential and logarithm for rotations. We can find a similar physical interpretation for the multiplication of T dot and T inverse as this equation. In the angular velocity section, we saw that the multiplication of r dot and r transpose is the symmetric matrix representation of the angular velocity expressed in the fixed frame coordinates. Now let's figure out what Vs means, which is obviously not the linear velocity of the body frame origin expressed in the fixed frame, which we know that it's equal to p dot. Suppose we have an infinitely large rigid body that the origins of the frames S and B are 2 points on this rigid body, and P is the location of the origin of the B frame relative to the S frame, as you can see in this figure. As the body moves, the origin of the B frame traces a circular path of radius P relative to the origin of the frame S. From the dynamics of rigid bodies, we can easily write the motion of the origin of the B frame relative to the motion of the origin of the S frame as this equation, where omega S is the angular velocity of the rigid body expressed in the frame S. Therefore, the cross product of omega S and P is the linear velocity of the origin of the frame B during rotational motion that is tangent to the circular path expressed in the S frame. Therefore, we can conclude that Vs is the instantaneous velocity of the point on the infinitely large rigid body currently at the origin of the S frame expressed in the S frame. With these definitions, the spatial twist, which is the spatial velocity in the space frame, can be expressed as this equation. And then the matrix representation of the spatial twist can easily be written as this equation. Note that here, as we discussed earlier, the bracket notation doesn't imply a symmetric matrix, but rather it only wants to show the 4x4 matrix representation of the twist. Also note that, like the angular velocity, for any given twist, its fixed frame representation is not dependent on the choice of the body frame, and its body frame representation doesn't depend on the choice of the fixed frame. From the equations that we obtained for the body twist and the spatial twist, we can find the relationship between them. The matrix representation of the body twist and the spatial twist will have this relationship with each other. Expanding one of the equations and inserting the values for t and t inverse, we can find the relationship between the spatial and the body twists. We saw that r bracket omega r transpose is equal to bracket r omega. And it's easy to see that bracket omega times p is equal to minus bracket p times omega for every pn omega in R3. It's easy to find because bracket omega p is equal to the cross product of omega and p, which is in the opposite direction of the cross product of p and omega. Inserting these into the matrix form of the spatial twist, we get this relationship for the matrix representation of the spatial twist. Therefore, we can write the relationship between the spatial twist and the body twist as this formula. This relationship is beneficial when changing the frame of reference for twists and wrenches that we'll study in the next lesson. Similarly, we can find the similar relationship for the body twist in terms of the spatial twist as this equation. Therefore, the relationship between the body twist and the spatial twist can be calculated with this equation. Note that both the body twist and the spatial twist represent the same motion, just in different coordinate frames. The matrix that can change the frame of representation of a twist or a screw is called the adjoint representation of a transformation matrix T. The adjoint and not the transformation matrix T is used to change the frame of representation of a twist because of dimension mismatch. This relationship is the modified version of the subscript cancellation rule to change the frame of representation of a twist. Now we want to officially define the adjoint representation of the transformation matrix T. If T is the transformation matrix representing the pose of the body frame relative to the space frame, then its adjoint representation is defined as the 6x6 matrix. For any twist, the adjoint map associated with the transformation matrix T is defined as this equation. And the matrix form of the adjoint map associated with T can be calculated using this formula. Now let's study the properties of the adjoint map. If T1 and T2 are two transformation matrices and the special letter V is the twist, then the adjoint map associated with the matrix multiplication T1, T2 can be calculated using this formula. The proof of this property is through direct calculation. And for any transformation matrix T, the inverse of the adjoint representation of the transformation matrix T is the same as the adjoint representation of the transformation matrix T inverse. To prove this, you can input T1 equal to T and T2 equal to inverse of T in the first property. Let's wrap up this section with 3 examples. Suppose that the body frame's x-axis is in the direction of the z-axis of the S-frame, and the body frame's y-axis is in the opposite direction of the x-axis of the S-frame. And the origin of the B-frame relative to the S-frame is 3, 0, 0. The twist is represented in the space frame as 3, 2, 1, minus 1, minus 2, minus 3. 3, 2, 1 is the angular component, and minus 1, minus 2, minus 3 is the linear component of the twist. We want to find the representation of the same twist in the body frame B. We just learned that the adjoint representation of the transformation matrix could be used to relate the spatial twist and the body twist. So the body twist can be found using this equation in terms of the spatial twist. Now let's see another example. Consider the motion of a 1 degree of freedom planar robot arm, as you can see here. The corresponding space and body frames are depicted in this figure. From the lesson about degrees of freedom, we learned that each rotational joint provides 1 rotational degree of freedom to the body that it connects. Therefore, theta is the angle of rotation about the reference configuration, that is 0 at time t equal to 0 and increases with time t. The pose of the end effector relative to the base frame can be found using the homogeneous transformation matrix T. The orientation of the body frame relative to the base frame can easily be expressed as the rotation matrix representing a rotation about the z-axis. In order to understand how to calculate this, please refer to the lesson about exponential coordinates of rotation and the rotation matrix lesson. And the position of the B frame relative to this frame can be calculated from geometry as this vector. From what we've learned so far about angular velocities and twist, we can calculate the spatial twist using this equation. Thus, the angular velocity expressed in the base frame can be calculated as 0, 0 theta dot. The velocity of a point currently at the origin of the S-frame expressed in the S-frame can be calculated as Vs equal to 0, 0, 0. And it means that the velocity of a point currently at the origin of the S-frame expressed in the S-frame is 0. And this is also understandable from geometry, and we'll see it shortly. Therefore, the spatial twist can be calculated as 0, 0 theta dot and 0, 0, 0. The body twist can either be calculated directly from the equations that we learned, or we can use the adjoint transformation to find the body twist. This result can also be verified from the direct calculation. The linear part is the velocity of the origin of the body frame expressed in the body frame coordinates. Theta dot is the joint speed, which shows the rate of change of the joint angle in this case. We can also verify the result geometrically. Suppose the 1 degree of freedom robot arm at 0 configuration. The 0 configuration is shown for simplicity. The linear velocity of a point at the center of the S-frame expressed in the S-frame is 0, since the radius of the point to the center of rotation is 0. On the other hand, the velocity of the origin of the body frame is tangent to the circular path and is at a radius of L from the center of rotation. Therefore, BB can be calculated as the cross products of omega B and the radius of rotation, and we can see that VB is in the y direction, and this was also predictable. Let's see another example. Suppose that a kid is sitting on a merry-go-round, spinning counterclockwise, and is at 10 centimeters from the center of the merry-go-round. The body frame's x-axis is pointing outward away from the center of the table, and its y-axis is in the direction of where the kid's eyes are looking. The z-axis is then pointing upward. The rate at which the table is rotating is 1 radians per second, so theta dot is equal to 1. We want to find the body twist, which is the angular velocity and linear velocity expressed in the body frame. This figure shows the sketch of the problem. The angular velocity is in the z direction of the body frame with the magnitude of 1 radians per second. The linear velocity is in the direction tangent to the circular path, so we already know that it's in the body frame's y direction. But we can also verify that by calculation. Imagine this linear velocity this way. During a circular motion, the centripetal force is in the direction of the center of rotation. If this force is eliminated suddenly, then the object spinning on the plate will move with the linear velocity in that direction. We already discussed this in the example of the salad spinner in the exponential coordinate of the rotation lesson. Therefore, the body twist can be expressed as the vector 001, 0.10. That's going to wrap up today's lesson. I hope that it gave you a good understanding about velocities and robotics. If you liked the lesson, share it with your friends who are in the same path as you to master robotics and mechatronics and help us in our mission to make robotics available to everyone. In the next lesson, we'll see how we can use a twist to define a screw motion. Stay tuned for the next lesson. See you in the next lesson. Bye!